Welcome, welcome, welcome. We've got general equilibrium, part 5. This is going to be a general equilibrium model of money. So previously, right, we've gone over general equilibrium models. We've played with them quite a bit at this point, not like super extensively or anything like that, but at least enough that maybe have some idea as to what's going on. But what we haven't done is applied any of these types of models to monetary economics. And since this is a money and banking course, it seems kind of important to, actually play with something that has money in it, right? So don't worry, it's not that big of a deal because really all you need to do is just put money in the models. And you're probably like, okay, great, what the hell does that all mean? Well, what we're going to do is we're really just going to be adding it to the constraint. We're also going to be adding a couple of other things for the government because this model is almost identical to what we had previously, but we're adding a government to it, right? And the government's functions are that it can tax, it can sell bonds, and it can print money. So the way it taxes is what's known as a lump sum tax. So this is not like, realistic in any particular measure here, but the way it would be is, say everybody just pays $100 in taxes every period, and that's it. Whether you're rich, whether you're poor, whether you're in the middle, everybody pays $100. So it's not even like a flat tax. That's still like, a percentage of what your income is. This is just everybody pays a lump sum, and that's it. Now, whatever they want to spend on top of whatever they've brought in via tax revenue, they have to sell bonds, right? They got to borrow the money. And they can also print money. And we'll get into the uses and all that stuff a little bit later. So let's get to the utility function. Now, the utility function is the same as what we saw before. It's utility being a function of current and next period's consumption. So we got the natural log of today's consumption plus beta times the natural log of future consumption. Remember, beta is that preference parameter for like your time price. It's a discount, right? It discounts tomorrow's or next period's utility by some amount between 0 and 1. It tells us basically what percent next period's utility is in terms of importance to this period. So the utility function's the same, but the constraint's a little different. This is the constraint. So you can see it's all color-coded here. Everything in the pink, with the exception of that tau term at the end, is what we saw in the previous model. Consumption is a function of output minus investment. So really all I did there is just sort of play around with that constraint y equals c plus I, right? I solved y equals c plus I for c, and then I plugged in y and I. So what do we have in the light blue? Well, that is the flow of money, right? That's money creation. What I have in the darker, a little bit more bold blue is the flow of bonds. And finally, I've got tau at the very, very end. Now, I've kind of already done a little bit of algebra and stuff like that. So really, it's like we're subtracting out the money flow and the bond flow equation. So really what it would be is, say, for money, 1 plus pi times mt plus 1 minus mt. But because it's on the other side of the constraint, it's being flipped around, so it's mt minus 1 plus pi t times mt plus 1. The same thing goes for bonds, right? So what we've got here really is a money flow and bond flow equation being substituted in. We've got taxes, so the money, the bond, and the tax stuff is the government's function. And then output here, tomorrow's capital and today's capital, right? It's like private sector function stuff. So what we've got, MT and MT plus 1 for today and tomorrow's money stock with an inflation rate of pi. Now, these are, real values of money. So this is the real money stock. It's not nominal. I've already controlled for the price level, hence why we've got that 1 plus pi times MT plus 1. What that's doing is that's essentially putting tomorrow's nominal money stock in terms of today's price level. So I've already controlled for inflation. Also, if you look at the bond flow equation, right, we have 1 plus the real interest rate. It's not 1 plus the nominal interest rate. So money and bonds, actually every variable here is already in real terms. So there's nothing that you have to do with trying to convert a constraint that's in nominal terms into real terms. I've already done that for you. So we've got BT and BT plus 1, which is today and tomorrow's bonds, that last one period. So each bond that you buy today matures tomorrow, and it matures with an interest rate, or a real interest rate, of R sub t. Now, money and bonds are both state variables, right? So we decide to hold MT plus 1 and BT plus 1 today, or in period T. And as I've said before, taxes are lump sum each period, right? So you can see, okay, we lose a little bit of like realism by making them lump sum, but the one thing that's really nice is they're being added in to the constraints, not being multiplied by like what your income is, for example. What is the benefit to that? Well, the benefit is the taxes here are non-distortionary. Because they're not distortionary, right? Once we take the derivative of this stuff, we do our utility maximization. When we take those derivatives, the tax term washes away, it goes to zero. So we're not having taxes distorting anything at the margin, because whenever we think about things at the margin, it's your first derivative. So if something differentiates to zero when you take that first derivative, it is thus non-distortionary. Okay, so previously, there were exchanges and transactions, right, with the previous models that we did, but they never had explicit prices. They didn't have money in either. Rather, money wasn't being used to facilitate the transactions. The previous assets had positive nominal and real returns, right? If we had capital, well, the investment in capital would have a positive nominal and a real return. Money, on the other hand, doesn't. But there's money demand in the real world. So if we were going to be including money here, we would have to have a positive demand for money, which makes it more realistic. We can't just assume everything away and have these totally unrealistic assumptions. There needs to be some degree of realism here. So hopefully the models can get a little bit more intuitive when we include money. So let's go through the setup. Right? We decide to hold bonds because they're an asset that pays off tomorrow at a real interest rate of R sub t. So it makes sense for why you would want to hold on to bonds, right? Because you're getting a positive real rate of return. Okay, that's good. Why would we want to hold money, though? Because money doesn't hold value, right? It actually loses value. If you've got $100 today and you decide not to spend it, right, you just want to hold on to that money, well, you'll still have $100 in the next period, but because of inflation, it's eroded away the real purchasing power of that $100. Let's say it's maybe $95, right? So you've lost a little bit of what you can do with that money just because inflation has eroded away the real purchasing power of every dollar. But we're going to hold money because it provides a valuable service to us. It lets us buy stuff. So we don't want to hold any more money than's needed, because as soon as we do, we begin losing more money than what we would otherwise, benefit from. And I know it sounds weird. It's like, okay, you're going to hold money and lose it, but you're going to benefit from doing so. Well, because it facilitates these purchases, right? It allows us to buy things. And because we value those things, we're willing to give up a little bit of our resources in terms of allowing inflation to erode them away, but we don't want to do it too much. Because if, say, I wanted to hold more in bonds or in capital, right, that would produce a real return, and I would be happy with that. It's got a real positive, or a positive real and nominal interest rate or return, right? So we don't want to hold any more money than what's needed, because you can have bonds and capital that would produce a real return for you. They're not going to be losing their value over time. So we want to hold just enough money to let us buy what we want, and then hold the rest as non-money assets, which generate a positive real rate of return. Okay, so here's the setup again. I was like, oh, here's the setup, and now here's another slide. Here's the setup. We got our utility function in equation 3. Equation 4 is the current period constraint. Equation 5 is the period 2 constraint. Notice in period 2, right, there's nothing that has an M or B or K or whatever sub T plus 2, because the world doesn't exist in period T plus 2, right? It's only period T and T plus 1. So when we look at that, right, we really just go through equation 4. we add 1 to every t subscript, and anything that's got t plus 2 just goes to 0 because, we're assuming the world ends after period t plus 1. And period t plus 2, there is no period t plus 2. It doesn't exist for us. So you want to go through and take a look at it, see what you got. Cool, be my guest. But these are the two constraints that you'll end up with. And what we're going to want to do is we're going to want to substitute the right-hand side of equation 4 in for CT in equation 3 right here. And we're going to want to substitute the right-hand side of equation 5 in for CT plus 1 here in equation 3. Now, I'm not going to be doing it explicitly in these slides because it would literally run over the edge of the slide. I'm doing the best I can here. But you should be able to see where things are going to be going. So what I'm doing is I'm just going to color code CT and CT plus 1 in this utility function, and I'm going to give you these two constraints underneath. So when you're taking notes, I would highly suggest you substitute this stuff here in equation 7 in for the pink CT in equation 6, and then this stuff here, right-hand side of equation 8, in for this kind of like teal-ish or turquoise, whatever it is, CT plus 1 in equation 6. All right, when you do that, you'll actually be able to see the whole thing written out. It's just to save space. I didn't do that. Now we're going to be differentiating equation 6 with respect to KT plus 1, BT plus 1, and MT plus 1. So we're going to have a couple extra derivatives here. The first order conditions we get. Well, when I take the derivative of that utility function with respect to KT plus 1, I get this right here, equation 9. I get negative 1 over CT plus beta times 1 over CT plus 1 times the marginal product of capital less depreciation, right? So this thing right here that you've seen is no different than the Euler equation that you saw in the previous models. So, you might be like, oh, well, it looks like there's a lot. There's really not, right? Because if you look here, okay, yeah, we have all these extra terms, but they're additive. So if you take the derivative of this thing with respect to KT plus 1, all right, everything that's MT, BT, tau T, that stuff just goes to 0, differentiates away. So this is telling us that even though there are bonds, money, and taxes in the model at the margin, we still make decisions for our capital holdings, right, our investment, via just this right here. Now we're going to do the same thing for bonds, and I get negative 1 over CT times 1 plus the real interest rate to the power of negative 1 plus beta times 1 over CT plus 1, and that's also equal to 0. I do the same thing for money. Negative 1 over CT times 1 plus pi plus beta times 1 over CT plus 1, and that is equal to 0. So with these three equations here, I have an Euler equation for capital, bonds, and money. So if I solve these guys out, right, I just move everything over to the other side, I get these three equations. So these right here are my Euler equations. So I have an Euler equation for capital, one for bonds, one for money. And we could go through all the general equilibrium stuff here, but really what's more interesting is what happens in the steady state, at least maybe for right now. But in the steady state, right, remember all endogenous variables grow at a constant rate. So it means that KT equals KT plus 1, both equal to steady state capital. Same goes for money, same goes for bonds, right? The super interesting stuff here is what happens with money when we're in the steady state. Namely, if any real variables are going to be affected by changes to the money supply. All right, so the idea is if we change the supply, will we have any effects on, say, capital or output? Well, in order to answer that, let's start with the Euler equation. The Euler equation for capital. So this is what we have. All right, I moved that 1 over CT plus 1 to the other side, so I get CT plus 1 over CT equals beta times the marginal product of capital less depreciation. And in the steady state, remember, steady state consumption is equal to CT equals CT plus 1. KT and KT plus 1 are equal to each other, which gives us steady state capital. So I just put SS subscripts in everywhere I see a T, and this is what I get. So I get steady state consumption over steady state consumption equals beta times the marginal product of capital less depreciation in the steady state? Well, CSS over CSS is equal to 1. Right, so that left-hand side just reduces to 1. Okay. I want to move beta over. Now, what I did here, right, is, remember, beta is 1 over 1 plus rho. So I just said, okay, well, beta is equal to 1 over 1 plus rho. Move beta to the other side. I get 1 over beta. 1 over beta is equal to 1 plus rho. So I get 1 plus rho equals the marginal product of capital less depreciation. Well, I'm going to subtract 1 from both sides, and then I'm going to add delta to both sides. So now I get rho plus delta equals alpha times A times K to the alpha minus 1. Divide both sides by alpha times A, so I'm isolating KSS. But in order to fully isolate KSS, right, first I'm going to multiply, or I'm going to raise both sides to the power of negative 1. So now I get alpha times A over rho plus delta equals KSS to the 1 minus alpha rather than alpha minus 1. And then I fully isolate KSS, steady state capital, and that is equal to alpha times A over rho plus delta to the power of 1 over 1 minus alpha. So we've seen this before. This is capital in the steady state. But here's what's cool, right? We've seen this before. So if we've seen this before, even though we've got money in this model, but it looks just like what we had in the last model, right? Do you see anything that says money would affect capital in the steady state? I don't. I don't at all. So what that tells me, right, is if we do change the money supply, it's not going to be affecting the capital stock. Maybe it'll affect steady state output, right? You never know. So let's say we get steady state output. We take steady state capital, plug it into K for the production function. Cool. This is steady state capital. I want to plug the right-hand side of what I have in pink into KSS in equation 17. Okay. Well, I get that. So that's my steady state output. Do you see anything for M in steady state output? Because I don't. So money doesn't affect steady state capital or steady state output. So if we look at the steady states for our two real variables, do we see money in any of these? I don't. There's no MSS, right? Steady state money. It's not in there. So that's kind of interesting, isn't it? Now here's what's interesting, right? Here's what's cool about this stuff. The steady state values of real variables are unaffected by changes to the money supply. Let's talk about some things. What is that? Do we remember what that is? Well, I guess I kind of skipped to the next item here on the slide, which is monetary neutrality. And model is said to exhibit monetary neutrality if before, right, I said it exhibited monetary neutrality if the long-run values of these things aren't affected by changes in the nominal money stock. But let's change that definition just a bit. Now, a model is said to exhibit monetary neutrality if the steady state values are not affected by changes in the nominal money stock. So in the steady state, if these things aren't affected, then they exhibit monetary neutrality. But they also exhibit monetary superneutrality, because if we were to change the growth rate of the nominal money stock, these real variables wouldn't change. So let's talk about something else, like how and why steady state capital is independent of the rate of inflation. So we're going to use the next slide for that, just to save some space and all that good stuff. So let's start with the Euler equation for capital. I'm going to flip it such that we get this right here. Why am I doing that? Well, you'll see why. From this, right, from equation 22, we see that it's equal to 1 in the steady state. So if, say, the current value of capital is less than what the steady state capital would be, the marginal product of capital right now is greater than the marginal product of capital in the steady state. So the right-hand side of equation 22 would be smaller than 1. But remember, if it was in the steady state, it would be equal to 1. So this is telling us that if I've got current consumption over future consumption, right, the marginal utility of consumption would be declining over time. Thus, if the marginal utility of consumption is declining over time, it would be optimal to postpone consumption to accumulate capital to have consumption grow over time. What do I mean? Well, if the current capital stock is less than what it should be, right? So think of like steady state capital being what it should be in the long run. If we have less capital than what it should be in the long run, then we essentially have a situation where we want to postpone our consumption to buy more capital to get it closer to that steady state. When capital is closer to that steady state or equal to the steady state, then consumption will actually be growing over time. Think of it like give up a little consumption now for a lot more later. So as long as the marginal product of capital less depreciation is greater than 1 over beta, this process is going to continue. Think of it kind of like a step staircase thing as we kind of converge towards a steady state capital. But as the capital stock grows, the marginal product of capital declines. And if you don't believe me, just, draw out what the marginal product of capital would be. As we increase the capital holdings, right, the marginal product of capital will fall. And it falls until that denominator of equation 22 is equal to the numerator of equation 22. So the marginal product of capital less depreciation is equal to 1 over beta. And consumption is only going to be constant when the marginal product of capital less depreciation is equal to 1 over beta. So from this, and continuing from the last slide, consumption's only constant when the numerator and the denominator of the right-hand side of now equation 23 are equal. So if there's an increase in the rate of money growth, let's say an increase in the rate of inflation, and it were to induce households to actually want to accumulate more capital, it would lower the marginal product of capital, and it leads to a situation where the marginal product of capital less depreciation is less than 1 over beta, which leads to households wanting their consumption paths to decline over time, which means households will increase their current consumption, and thus future consumption would fall, reducing their holdings of capital, right? So as we can see here, right, it would have like a change like in the short run, but in the long run, what we trend towards, that steady state capital, would still be independent of the rate of inflation. And while this says slide 19 out of 33, it's actually the end. This is slide 19. This is the last slide of this lecture. So we will wrap up. Well, I've got 2 more lectures after this covering general equilibrium models of money. But for now, I'll end it here, and we can go a little bit further in the next presentation. So thank you for watching, and I will be explaining some of this stuff in a little bit greater detail, and hopefully in a slightly more intuitive and easy to digest manner if this one is a little bit tricky for you. So if you're a little confused, don't worry. We got more good stuff coming in the next video, so stay tuned. Thank you for watching.